Experiments at NIST, we first look at the fuels that we're going to put into the apartment that we're going to build. And so how are we going to start our fires? Now, we want to do things very repetitive so we can repeat them one experiment after another. And so the first thing we do is we're going to start our fires with a trash can. Little small plastic container. We put a little bit of newspaper in it, light it on fire with an electric match. You can see it burning there in the top image. That's around 30 kilowatts, 30, 40 kilowatt fire. Pretty small fire. We light a chair. We get a number of identical chairs. Basically, we have 2 tractor trailer loads full of furniture from an old hotel, roll up to NIST, and that's what we're using. So we have replicate furniture for each of the 8 apartments that we're going to burn. And the chairs are giving us 1.8 megawatts, or 1,800 kilowatts, 1.8 megawatts. And you see the chair in the next picture down. And that's quite a bit of fire coming off of it. So if you imagine one of those chairs in your house and you have 6-foot flames coming off of it, imagine that in your living room. Then we go to the sofa, and these were hotel sofas from a hotel, so they don't have a lot of plush padding on them, but they're still not too bad. 2.5 megawatts was the average peak heat release rate that we're getting off the sofa in this image here. The bed, king-size bed, very comfortable, very plush, fully involved, little over 4 megawatts of energy. Anybody know what it would take to flash over a room, typical residential scale room? Around 2 megawatts. So basically, 2 chairs, more than enough, or maybe even 1 chair with a little bit of latex paint on the walls would be good enough for some carpeting. 1 sofa or half a mattress would be enough to generate enough energy to flash over a typical residential scale room. Fire intensifies again. Smoke is fuel. Right? If we're controlling the oxygen, and that's how we're going to control the fire, you've got to keep that vent closed. But you still have the fuel in there. It's still pretty warm. Now how are we going to cool it? This is another view of that same test again, just to sort of watch the area around when our window breaks and look what's going on at real time in the corridor. And one thing you notice is the flames typically have to impact the window, touch the window to transfer enough energy to the window to get it to fail. But before window failure, again, things aren't bad. But as soon as the window fails, things go bad in that corridor very, very quickly, within seconds. And as was alluded to before, this is the kind of situation where you're going to go down to cover up and you're not going to get back up. It happens so fast. It's transferring so much energy to you. And what's going on with the fire? We're blowing in there 15, 20 miles an hour, and yet the flames are still coming back against the wind. This is exactly what the roof man in Vandalia saw. But we didn't understand it at the time. We didn't understand the issue with the overpressure. Here's test 7, just a small clip. Again, the fire's building up. We fail the window. Here, the door to the corridor is closed. So what you see now are leaks around the door, a small opening in the keyhole, and you see how hot gas is being pushed under the door, around the door. We still have flames blowing back out. Now, what we're going to do is we let this happen for a while, and then we're going to open the door. So this shows you that there are some things you can do to move your hand around. Even if you can't see, it's better if you have a thermal imaging camera. Obviously, you'll see something like this. But don't just go opening doors. Or if you open doors, only open them a little bit, especially on a windy night. Open the door fully, boom, untenable conditions in the corridor within seconds. Engineering terminology. What does that look like for temperature? What I've got here are temperatures in the bedroom, top line, the living room, the next line down, corridor south and corridor southwest. Those are the areas that do not have flow, the non-flow side, and then corridor north is the flow side, and that's this line here. Time 0 is when we open the door. So we can see that opening the door not only affects conditions in the corridor, these 3 portions of the graph, but also affects the temperatures in the bedroom as well. Initially, it cools things off. A lot of fresh air comes in. It's fuel rich, and then the fuel and the air mix come together, and we go from conditions that are under 600 degrees centigrade, or basically under 1,000 degrees, and then jump up to things that are in excess of 1,500 degrees F. Notice that the living room follows suit, and the flow portion of the corridor tracks with them very well. The non-flow portion of the corridor remains at a much cooler temperature. Many of the line of duty death incidents that we work with NIOSH and other fire departments to investigate end up with a condition where the firefighters ended up between the fire and where the fire wanted to go. And that's a bad place to be. And in many cases, they ended up in that position based on how the fire department vented the building, or doors that they opened, or a flow path that they made. So what do we learn? Well, we have an idea what some of the heat release rates are from some different kinds of upholstered furniture. We demonstrated some basics. Smoke is fuel. Venting does not always equal cooling. Right? When the window broke, did conditions get cooler inside? No. Temperature increased, energy increased. Be aware of the flow path. Where is it? And control it or stay out of it. Control the doors. Whether you're controlling the door at the stair, open it just a crack and see what's going on. Wind-driven fire flows generated untenable conditions for fully protected firefighters in a very short period of time.